Hello. Our discussion today will center on wave-particle duality and the role of Einstein and Compton. In 1907, Einstein applied for a pre-docent position. As I've already mentioned, this venia docendi is a license to teach at a university and does not carry any salary. The subject of Einstein's Habilitationsschrift was Consequences of the Constitution of Radiation of the Energy Distribution of Blackbody Radiation, and on February 28, 1908, he was informed that his application was approved. He was now a member of the academic community, and he started teaching classes after regular hours at the University of Bern while still continuing his job at the patent office. In January 1909, Einstein derived his energy fluctuation formula, a relationship now well known in statistical mechanics. For a cavity of volume V, we have the average energy being given by ρ times V times d nu, where ρ is the energy density per unit volume in the frequency interval nu to nu plus d nu. So that gives for the fluctuation, for the energy fluctuation, kT squared times V d nu del rho by del t. But using the Rayleigh-Jeans law for the energy density, which is based on the classical wave theory of light, we get this formula, whereas using the Wien's law and the light quantum hypothesis, we get the second formula. And Planck's law gives this equation. So we see that the Planck's law is a combination of the classical wave theory of light and the light quantum hypothesis. Einstein also derived an expression for the momentum fluctuations. Einstein thus concluded that our current foundations of the radiation theory have to be abandoned. It is my opinion that the next phase in the development of theoretical physics will bring us a theory of light that can be interpreted as a kind of fusion of the wave and emission theory. By emission theory, he meant the Newtonian corpuscle concept. The wave structure and the quantum structure are not to be considered mutually incompatible. This goes by the name now of complementarity. But although Einstein obtained a relation for momentum fluctuations in blackbody radiation, the first explicit identification of a photon momentum was made by Johannes Stark in 1909. In his words, the total electromagnetic momentum emitted by an accelerated electron is given by h nu by c. In 1909, Einstein obtained an associate professor position in theoretical physics, a newly created position at the University of Zurich. Alfred Kleiner's recommendation for this position states, "Today, Einstein ranks among the most important theoretical physicists and has been recognized rather generally as such since his work on the relativity principle." The faculty report accepting the recommendation nevertheless betrays views typical of European civilization in the early 20th century. These expressions of our colleague Kleiner, based on several years of personal contact, were all the more valuable for the committee, as well as for the faculty as a whole, since Herr Dr. Einstein is an Israelite, and since precisely to the Israelites among the scholars are ascribed, in numerous cases not entirely without cause, all kinds of unpleasant peculiarities of character such as intrusiveness, impudence, and a shopkeeper's mentality in the perception of their academic position. It should be said, however, that also among the Israelites there exist men who do not exhibit a trace of these disagreeable qualities, and that it is not proper, therefore, to disqualify a man only because he happens to be a Jew. Indeed, one occasionally finds people also among non-Jewish scholars who, in regard to a commercial perception and utilization of their academic profession, develop qualities which are usually considered as specifically Jewish. Therefore, neither the committee nor the faculty as a whole considered it compatible with its dignity to adopt anti-Semitism as a matter of policy, and the information which Herr colleague Kleiner was able to provide about the character of Herr Einstein has completely reassured us. The secret faculty vote of March 1909 records 10 in favor and 1 abstention. On July 6, 1909, Einstein submitted his resignation to the Swiss Patent Office in Bern and moved to Zurich, where he taught for the next 2 years. In March 1911, Einstein moved to Prague with his wife Mileva and 2 sons to take up a full professorship there. He would stay there for 16 months. In between his heavy teaching schedule at Zurich and Prague, Einstein continued brooding on light quanta. In May 1911, he wrote to his friend Bessel, "I do not ask any more whether these quanta really exist, nor do I attempt any longer to construct them, since I now know that my brain is incapable of fathoming the problem this way." On June 12, 1913, Planck, Nernst, Rubens, and Warburg signed a formal laudation recommending Einstein for membership in the Prussian Academy of Sciences. The vote of the Academy was 20-1. This was combined with an offer of professorship at the University of Berlin with the right but not the obligation to teach classes, and the directorship of a new physics institute at the Kaiser Wilhelm Gesellschaft. In March 1914, Einstein left Zurich and moved to Berlin. Soon after moving to Berlin, the Einsteins separated and Mileva returned to Zurich with their 2 boys. On November 25, 1915, Einstein presented a paper to the Prussian Academy of Sciences on the field equations of gravitation. Thereafter, he returned to work on light quanta with a new derivation of Planck's radiation law and wrote to Bessel in November 1916, "A splendid light has dawned upon me about the absorption and emission of radiation. If radiation of the appropriate frequency is incident upon a molecular system with electrons in definite energy levels, then a molecule in the lower electronic state with energy E1 can absorb the radiation and make a transition to the upper energy level E2. The radiation can also induce a molecule in the upper energy level to emit another photon of frequency nu and transition to the lower energy level. Of course, even in the absence of radiation, a molecule in the upper energy level E2 can spontaneously emit a photon of frequency nu and transition to the lower energy level. Now, the rate of absorption is proportional to the radiation density rho at the appropriate frequency nu, and also proportional to the number of molecules N1 in the lower energy level. The proportionality constant B12 is known as the Einstein transition probability for induced absorption. Likewise, the rate of emission is the sum of the rates due to stimulated emission and spontaneous emission. Here B21 and A21 are the Einstein transition probabilities for induced emission and spontaneous emission respectively. Now, at equilibrium, that is steady state, the rate of absorption is equal to the rate of emission of radiation, and therefore equating these two terms, we get N2 A21 plus B21 rho equals N1 B12 rho. According to the Maxwell-Boltzmann distribution, the populations of molecules in the two states are inversely proportional to the exponentials of the respective energies. Therefore, the ratio of the number of molecules in the upper energy level to that in the lower energy level, that is N2 by N1, is given by e to the power minus E2 minus E1 by kT. Now, the number of molecules in the lower energy level is greater than the number of molecules in the upper energy level, and therefore the rate of absorption of radiation will be more than the rate of emission. And so if we shine intense laser light for a long time, the more and more molecules will go from the lower energy level to the upper energy level, and eventually the populations of the molecules in the two states will equalize, that is N2 equal to N1. This is called saturation, that is, there is no more net absorption of radiation, and it corresponds to infinite temperature, because if you look at this equation, N2 is equal to N1 when T tends to infinity. Now, substituting the expressions for n1 and n2 in the first equation, we get this equation, and rearranging this equation, we get P2A21 is equal to rho times P1B12 e to the power E2 minus E1 by kT minus P2B21. Without the second term on the right hand side, that is the induced emission term, the B21 term, we get Wien's law. For fixed energy difference and infinite temperature, we should get the Rayleigh-Jeans law. Therefore, putting P1 B12 equals P2 B21, we get this expression for rho, which we see is Planck's law if we make the identification that E2 minus E1 is equal to h nu, that is the resonance condition. Therefore, we see that Einstein was able to derive Planck's equation starting from the Bohr's stationary state requirement. By 1917, light quanta had become real to Einstein. As he wrote in a letter to Bessel, "I do not doubt anymore the reality of radiation quanta." But around the same time, we see the first expressions of his Unbehagen, or discomfort, in regard to the role of Zufall or chance. For in spontaneous emission, the molecule suffers a recoil h nu by c, but the direction of recoil is unpredicted. In Einstein's words, it is a weakness of the theory that it leaves the time and direction of elementary processes to chance. What defines when the photon is spontaneously emitted? What decides in which direction it will go? Of course, the same problem holds for the spontaneous emission in radioactive decay. Einstein was the first to realize that the probability for spontaneous emission is a non-classical process. This would lead to his subsequent misgivings regarding the statistical formulation of quantum mechanics in later years. As we saw, Einstein's 1905 postulate was that every light quantum has a definite energy E equals h nu. But in his 1916 and 1917 papers, Einstein postulated that a photon is a state of the electromagnetic field with a definite frequency nu and a definite wave vector k, an energy given by E equals h nu, and momentum given by P equals hk, satisfying the dispersion law E equals Pc. Note that the name photon was given to the light quantum by the physical chemist Gilbert Norton Lewis only in 1926. I use boldface here and in subsequent slides to represent vector quantities. The dispersion law comes from the Einstein's mass-energy relation, which is popularly known as E equal to mc squared for a stationary particle, but the full form is E equal to square root of p squared c squared plus m0 squared c to the power 4. But since the rest mass of the photon m0 is equal to 0, that reduces to E equal to pc. Arthur Holly Compton's experiments on scattering of X-rays between 1923 to 1924 led to definitive confirmation of the fact that photons are endowed with not only definite energies but also definite momenta. Until then, the scattering of high-frequency radiation was treated using J.J. Thomson's theory, which was based on Maxwell's electrodynamics. But several experiments between 1913 to 1920 showed the inadequacy of this theory for very short wavelength X-rays and gamma rays, for which the intensity of scattered rays is much less than predicted by Thomson's theory. Compton wondered what would happen if each quantum of X-ray energy were concentrated in a single particle and would act as a unit on a single electron. In Compton scattering, part of the X-ray photon's energy and momentum will be transferred to the electron. The scattered photon will thus have a lower energy or a longer wavelength. Arthur Compton and Peter Debye in Zurich independently derived the relativistic kinematics for the scattering of a photon of an electron at rest. Using the conservation of momentum, we get hk equals p plus hk dash, where p is the momentum of the electron, and by using the bold type I refer to vector quantities. And from the conservation of energy we get hck plus mc squared equals hck dash plus square root of p squared c squared plus m squared c to the power 4. On the basis of this quantum corpuscular model and using the conservation of energy and momentum, Compton then derived his famous formula for the change in the wavelength delta lambda equals h by mc into 1 minus cos theta, where theta is the scattering angle, and a similar equation for the angle of recoil phi. With the K-alpha line of molybdenum as the X-ray source and graphite as the scatterer, Compton measured the angle dependence of the scattered radiation at the Washington University at St. Louis and reported his results, which were in complete agreement with his formula, at the April 1923 meeting of the American Physical Society in Washington, D.C. In his paper entitled Wavelength Measurements of Scattered X-rays in the Physical Review, he stated, "The present theory depends essentially upon the assumption that each electron which is effective in the scattering scatters a complete quantum. It involves also the hypothesis that the quanta of radiation are received from definite directions and are scattered in definite directions. The experimental support of the theory indicates very convincingly that a radiation quantum carries with it directed momentum as well as energy." This discovery created a sensation among the physicists of the time. Compton's experimental results were confirmed by Ross at Stanford, Maurice de Broglie in Paris, and eventually even by William Duane at Harvard, who was initially a staunch critic of Compton at the December 1924 meeting of the American Physical Society in Washington, D.C. Meanwhile, in 1921, Emden had shown that the quantum corpuscular theory of light accounted for not only the Stefan-Boltzmann law and Wien's displacement law and Planck's radiation law, but also for the Doppler effect. This was also shown rigorously by Schrödinger in 1922. If a light quantum h nu is emitted in the direction of motion of an atom of mass m, v1 is the velocity of the atom before the emission and v2 is the velocity after the emission, conservation of energy requires h d nu is equal to half m times v1 squared minus v2 squared, while conservation of momentum requires mv1 equals mv2 plus h nu by c, which implies that d nu by nu is equal to v1 plus v2 by 2c, which is the Doppler formula. But other phenomena such as interference and Fresnel diffraction could be explained only by the classical wave theory of light. This led Sir William Bragg to remark that physicists are using the classical wave theory on Mondays, Wednesdays, and Fridays, and the quantum theory of radiation on Tuesdays, Thursdays, and Saturdays. Not a very satisfactory state of affairs. Well, has anyone been keeping track of the time? We are at 1924 in our story, and next year is the birth of quantum mechanics, and that's what we will deal with next week.